Let's do a fluid flow example. I'm sorry the blue is fading on us here. We have water at a gauge pressure of 3.8 atm at street level. It flows into an office building with a flow rate of 1.178 times 10 to the negative 3 cubic meters per second. So that's volume per time. It's flowing through a pipe that's 5 centimeters in diameter. The pipe tapers down to 2.6 diameters by the top floor, which is 20 meters above ground level. Want to calculate the gauge pressure in the pipe on the top floor. Now we're assuming there's no branch pipes, which really isn't a good assumption in an office building, but we don't want to worry about all the branches at this point in time. And we're ignoring any viscosity of the water, which that's an okay assumption. Water is not very viscous. So basically, we have a pipe down here. Somehow in the process of getting to the top floor, it's 5 centimeters in diameter down here. It's only 2.6 centimeters in diameter up here. The gauge pressure down here is 3.8 atm. We want the gauge pressure up here. Now remember, gauge is a difference. This will be the pressure at this point, P1, minus P naught of the atmosphere. Gauge pressure is a difference from inside to outside. So we want the same thing here. We want the pressure up here, let's call it P2, minus P naught. We want the gauge. Now fluid flow, there's a couple of equations that should come to mind. The first is Bernoulli's equation, which is the conservation of energy equation. I guess we used Y's, not H's. Let's use the Y. Bernoulli's equation tells us that the pressure plus the gravitational potential energy plus the kinetic energy has to be constant within any one given pipe. So P1 plus rho g y1 plus 1/2 rho v1 squared has to equal all the same stuff at point 2 in our pipe. Now P1 and P2 are the absolute pressures at those points. So P1, if we were to solve for P1, it would be the 3.8 atm plus P naught. You right with that? So the absolute pressure at that point would be 3.8 atmospheres plus 1 atm, so basically 4.8 atm. Is that legal? Add P naught to both sides. By adding P naught, actually, how about we subtract P naught? Because P1 minus P naught is the gauge pressure. P2 minus P naught is the gauge pressure. So if we subtract P naught from both sides, these now will be gauge. So we can just use our gauge values. Now with gravitational potential energy, the rho g y, we can, just like we did when we did energy problems before, we can choose y to be 0 wherever we want. So if we call the lowest point to be y equals 0, so y1 be 0, what will y2 be? meters. So y1 is 0, y2 is 20 meters. This is what we're looking for. We know this. We know this. We need to figure out the speeds in order to finish the problem. We need to know how fast the fluid is moving. Our other equation that we have for fluid flow is the flow rate. Remember, flow rate Q is volume per time. That is the 1.178 times 10 to the negative 3 cubic meters per second. So we know the flow rate. Flow rate is also equal to cross-sectional area times speed. So V1 will be Q over A1. We know Q. Q is the same everywhere in the pipe. A1, pi radius squared, we know the diameter, so it'll be diameter over 2 squared. V2 will be similar, only we'll need diameter 2. So A1, we're dealing with 5 centimeters, so 0.025 squared. So the water is flowing at 0.6 meters per second down in the 5 centimeter tubing, piping, whatever you want to call it. Do you expect it to be moving slower or faster at the top?
Faster.
Faster. If it narrows down. So, let's see, half of 2.6, 1.3, so 0.013 squared. So 2.22 meters per second at the top. So by knowing the flow rate, knowing the volume per time, we were able to figure out how fast the fluid is flowing in the different parts of the pipe. We can bring that back now. We're looking for this gauge right here. So I'm going to bring the other stuff to the other side. So I'm going to call this gauge 1. Gauge 1 plus 1/2 rho V1 squared minus rho G Y2 minus 1/2 rho V2 squared is equal to gauge 1. Or sorry, gauge 2. Now unit-wise you need to be careful. Our density of water is 1,000 kilograms per cubic meter. When we multiply that by the speed in meters per second, this quantity here is going to have units of newtons per meter squared, which is a Pascal. This term as well is going to have units of pascals. I'm going to erase this right here so we have room. Gauge 1, the 3.8 ATM. All of these terms that I've written, the 1/2 rho V squared and the rho G Y's, have units of newtons per meter squared, or pascals. Our gauge pressure is an ATM. We can't add atmospheres to pascals. It's not legal. That would be like saying 10 feet plus 2 centimeters is 10.2 centimeters. That doesn't work. We need to have common units. So we need to convert this to pascals, which is easy enough. We know there's 101,300 pascals per ATM. So it's easy enough to convert. Now to plug and chug all of this. So 3.8 times 101,300 plus Those of you plugging and chugging, are you getting the same value as me? Now we can easily put this back into ATM by dividing by the 101,300. So the gauge pressure at the top is only 1.8 ATMs, whereas at the bottom it was 3.8 ATMs. Why is the pressure lower?
Gravity.
Going faster and gravity. So both. The fact that it's higher and it's moving faster. Both contribute to the fact that the pressure has to go down. Questions? So it is common to need to use the flow rate equation as well as Bernoulli's equation in the same problem. The flow rate will allow you to find out how fast your fluid is moving in any cross-sectional area of pipe. And then Bernoulli's equation allows you to relate the pressures and the speeds and the heights all together in one equation.